I hope to see you in person.
Soon.
Yes. So you just in this talk, we are going to see some satellite imagery. We're also going to see some optimization visualization. But before I jump to those things, before those things come up, that's like a teaser. Um, I just want to tell you, just study all kinds of things in the space of design and sculpting and drawing and painting and a little bit of singing, color and motion. So all kinds of things in computer graphics and creativity. And this talk is about things related to motion, in particular this hyperspectral inverse skinning. But as a professor, much of the work that I do, most of the work that I do, all of the work that I do in a sense is the work of my graduate students. And so I just want to call out the student who, if it weren't for this student, the student did most of this work. And this student, if it weren't for him, if it weren't for Sangre and Leo, then I wouldn't have ended up in this direction at all. So I'm grateful to Sangre and Leo, who's graduated and Dr. Sangre and Leo, and as a researcher in industry. So with all that said, this brings us back to hyperspectral inverse skinning, which was a collaboration with Sangren Liu, my other PhD student, Jianqiao Tan, and Zhigang Deng at the University of Houston. And the subject of this, of this presentation, the subject of all of this is a form of motion, linear blend skinning. And here I've written down the formal equation, but I'll visualize it to put us all in this frame of mind. So in linear blend skinning, it's a way to animate or deform a shape or a character. And in this example, we are deforming a bunny. And we're going to place handles in this bunny. Now, these handles could be line segments, they could be points, they could take really a number of different forms. Here they're visualized as like a skeleton of the bunny. And then each bone in the skeleton, each handle is given a spatially varying weight across all of the entire surface. And then the weights have associated with them a transformation matrix, like a rotation here. We see that the elbow has a lot of influence on the hand and the forearm. And we see here that the transformation matrix associated with the elbow is rotating. And so the skin just takes this blended average transformation, and we see that we get this animation. And this is very nice. This is very simple, very straightforward. It's just a weighted average of transformation matrices. Because of this simplicity, it's an efficiency. It's also quite ubiquitous. You'll see this in games, and you'll see this, because where high performance is important. This is also used in films where I don't know, the efficiency and the controllability is valued. There are other forms of skinning, but this is a very common one. This is sort of I guess the default one. Now, in this talk, what we are going to do is we're going to flip the air around. So the idea is, well, if we observe motion, can we figure out what the weights and what the handles should be for it, and what the transformation matrices? So we're given a moving mesh, and we don't know any of these other forms. We don't know any of these other terms, and it's an underdetermined problem. We can have a small number, a large number of handles. We could have different kinds of handles, different kinds of weights, and different transformation matrices, which will all look the same. So we want to solve this problem in a way which recovers mesh and recovers it accurately, and hopefully has a few small number of handles. We didn't invent this inverse linear blend skinning problem. This is not a new problem. We can take this formula. This is a kind of a just to write this in a sort of least square sense. We can take this formula and we can replace the equal sign with the minus sign, with a subtraction, and then we can say we want to minimize this difference. So we want what we observe to look like what we recover across all poses that we've observed, and we want those weights, the influence weights, to sum up to 1 and be greater than or equal to 0. These are fairly standard constraints just to make sure that the weights are um, convex, the weights are convexly combined, the transformation matrices. And so, yeah, we can see previous work dating back to 2005 on this problem. So what I'm going to tell you about now is like a different way to look at this problem, and vexingly some open problems that result at the end. I'm not going to present to you a solution that I'm satisfied with, but it's a solution it's satisfying in its own way. Okay, so the point of view that I want to present is that we can view this inverse linear blend skinning as a problem in high dimensions. And I'm going to write down, I'm going to try to give some intuition here. So these transformation matrices, there's 12 numbers in an affine transformation matrix. So we can think of a transformation matrix as a point in 12-dimensional space, which I can't visualize. When we observe the mesh in a variety of poses, when we observe an animation or just poses, what we know is that these transformation matrices, there's one for each pose. So if there are p poses, now we have a 12p dimensional space. So each one of those handles has 12p numbers associated with it. So we can think of these handles as 12p dimensional space. So again, let's try to visualize this as best we can. Here is our 12p. Here we see some different various poses of a bent rod. And we can see that there are 4 bones. So there are 4 handles. And each of these handles, the first bone here, the first segment here, has its transformation across all the poses, and that is a point in this high dimensional space. Now, what we know because of linear blend skinning takes weighted averages of these transformations. So if we have 4 handles, then we have 4 points in 12p dimensional space, and the space of all possible transformations that we can apply at any position on this shape is a weighted average of these transformations. So to bring this together geometrically, what we can see is that the handles here are forming a simplex. We have 4 handles, so the weighted average, where the weights sum to 1 and are greater than 0, this is a simplex. This is a tetrahedron in this case, because there are 4 of them. So it's a tetrahedron in 12p dimensional space. We know the vertex transformations at any point have to lie inside this simplex, and the weights in this case are simply the barycentric coordinates. So if we knew the transformation, if we knew what these transformations were for the handles, then any point inside we know the weights, which are simply barycentric coordinates. Okay, so this kind of intuition brings us to our approach. So first, we want to estimate vertex transformations in 12p. But we don't know what the handles are. We're going to try to recover handles, but we do observe vertices. We observe this mesh in various poses. So with these observations, we're going to estimate the transformations applied to those vertices in every pose. So those are points in 12p dimensional space. Then we're going to estimate a subspace that covers all of those observed transformations, and so that's a subspace. And in that subspace, we just need to find a simplex, a nice simplex, which encloses it. So those are the 3 steps: estimate transformation matrices for the vertices, estimate a subspace that they lie on, and then find a simplex. Okay, so let's start with the first 2 steps, which we kind of handled together. All right, so estimating vertex positions in R12P. So we know for each pose, we know the vertex is the rest and the deformed position, and so we can write this uh, um, in a sort of a matrix form, and that's what we're seeing here. We're seeing that all of the vertex positions that we observe end up inside of this big V matrix, and then X is the transformations that are applied to it. X is the point in 12p dimensions. Um, I'm bringing up this term flat, and I'm going to tell you about flats, which, yeah, so let me kind of explore what these things are. So uh, flats generalize a line or a plane in higher dimensions. So this is the same thing as an affine subspace. It's a linear subspace offset from the origin. So it's a very simple idea. A line and a plane are very simple ideas. In higher dimensions, they behave a little more strangely, or at least it's a little less intuitive. Uh, um, And there are a few ways we can define these. So in the right here, what we're seeing is R3. I'm visualizing R3, three-dimensional space. I can visualize that because I live in it, I exist in it. And so in R3, we see a line, and this line is a one-dimensional flat. And so this one-dimensional flat, this line, we can think of it as P, a point on the line, plus B, which is a direction along the line, times some unknown quantity z. And with that, we can parameterize the entire line. This is fairly natural for us. The same thing works in higher dimensions, where the columns of B simply span the linear subspace offset from the origin. Yeah, and in that case, z would be a kind of vector of parameters, but that's straightforward. We can also define a flat as a weighted average. So in this case, the columns of f are just points on the flat, and the parameters sum to 1. So this is like we would have 2 points on the line, and we would say any combination of those 2 points that sum to 1 is a point on the flat, and that works uh, um, to also define planes or higher dimensional flats. And then finally, we can define a flat implicitly, and that's what we're visualizing here with this plane. To do this, what we need are the orthogonal directions to the flat. So if we're interested in the line, we can also represent this line by storing its orthogonal directions. In this case, it's dimensions. A plane is orthogonal to a line. So if we have the orthogonal directions to the line, in this case, A1 and A2, those are the rows of A. And so the rows of A times X define the flat implicitly so long as AX equals some constant A. So these are 3 ways to define flats. This is quite abstract, but it'll come in useful. It'll be useful for us. So the first step that we need to do is to estimate a flat that intersects or is as close as possible to all of these individual vertices flats. So we observe every vertex. We observe its motion across all the poses. So that gives us, we know that there's some unknown 12p dimensional point that will make this vertex appear in all the ways that it's appeared across all of these poses. So we just have a bunch of flats for for each of the vertices. Because there's not just one solution, there's not just one transformation matrix that will do this. So so what we're looking for, though, is if we know that this if we I heard an echo for a second, but that's fine. Each vertex is giving us some possible subspace, and we're looking now for a lower dimensional space that can satisfy all of these vertices, because we know that because we're defining our problem as saying this cylinder was deformed by four line segments, by a connection of a skeleton with four handles. So these four handles have to be enough to represent the entire, all of the observed motions of all the points on the cylinder. So this brings me to a problem that's fairly easy to specify, but it's fairly crucial for us, which is to say we want to find, given a bunch of flats. So in this case, like given a bunch of lines given a bunch of flats, find a flat which minimizes the distance. I'm going to illustrate this here because it's a very kind of nice subproblem. So in this case, let's just generate a bunch of 3D lines, and we know these 3D lines intersect a known line. We're going to generate these lines in space with a known ground truth solution, and we're kind of visualizing. I've generated a bunch of random lines, and we're looking down the solution space. So I generated a bunch of lines that all pass through the line, this kind of diagonal of the cube. If you can see this cube here. And we want to know if we can recover this ground truth line from some random initial guess. And so this is like, given a set of lines in 3D, find the closest line to this set of lines. Closest line being defined as you can take any 2 points on those lines. And here we're seeing this optimization happen. We're seeing this random purple line appears and starts to move until it becomes a point at the origin, and so it essentially disappears. And we can see here, we can rotate, and we can see all of these lines. All of those lines are that purple line is passing through all of the other lines. So that's nice. That's nice. If we could find that, if we had an optimization that always worked as well as this in our higher dimensional analogs, which are hard to visualize, then we would have fantastic solutions to this inverse skinning problem. So that's a great success. Let's look at higher dimensions where we can't easily visualize things. So here's an experiment in 24 dimensions where we're just going to generate a bunch of flats with some dimension d that intersect some known flat of some other dimension k. And we're going to see if we can recover the k-dimensional flat from a random initial guess. And so here's like a visualization of this. This is a visualization of the solution error and the number of iterations. So this is telling us like how successful we were at solving this problem. Yeah. So what do we see here? When d equals 0, the given flats, the given data are points. So right here, this bottom green row, we're given a bunch of points, and someone says, find me the closest point to this set of points. Easy. Find me the closest line to a set of points. Find me the closest plane to the set of points, and higher dimensional versions of that. And that's an easy problem. It becomes a simple least squares problem. What we also see that when d plus k is greater than or equal to our ambient dimension, it becomes trivial. This is like saying in 3 dimensions, find me the plane closest to a set of lines. A random plane is almost surely going to intersect every line. It's very, very rare to not have that happen. So no iterations are needed. 1 iteration is sufficient. The initial iteration is fine, and we get 0 solution error. When d plus k is less than 24, there's this like this bottom left corner of this triangle. There's this like difficult zone as d plus k approaches 24. I don't know why it's I don't know why it becomes so difficult. I know. I mean, I can describe. It's sort of known that this problem is. It's not convex. We can set up scenarios where there's multiple local minima, but sometimes we find great solutions. Like we converge to essentially the correct answer. but as we approach this diagonal, it gets quite difficult. We tried many possible ways to solve this problem, computing gradients, Hessian-based optimizations for explicit representations of the flat, optimization on the graph manifold, the space of rotations, optimizing projection matrices, basin hopping, global optimizations, looking at the Karcher means, um, and various other optimization strategies. And there's an appendix in the paper we have on this, how not to minimize flat distances, and you can read about the details of these other approaches. But the one I'm going to tell you is one that works pretty well, but it's somehow still not satisfying for me, and hopefully it won't be satisfying for you. And then hopefully you also take on this problem, which is a easy to define geometric problem that doesn't have a great solution. Okay, so let's get back to our animation setting. So we have a bunch of meshes, and these meshes, we have the vertices on these meshes, and we see that they we see them in different poses. So if a vertex and its one ring move rigidly, then we know what transformation was applied. If we see a vertex and its one ring in one pose, and we see a vertex and its one ring in another pose, there's a rigid transformation that takes it from one to the other. Then there's essentially a unique solution, particularly if we assume surface orientation. So if there's not a rigid solution, then we can still try to measure error in a least squares way. So this is just writing. This is the expression for a transformation matrix, which minimizes the error when applied to a vertex and its one ring. And we can measure the error in 3D or in this 12p dimensions. Measuring it in 3D is the error that we see, so that's also fine. The difference is small. And estimated this error for all of the vertices. Once we've estimated these transformation matrices for all of the vertices, we end up with a bunch of points in 12p dimensions. And we can run PCA on this, principal component analysis, and that will give us an we can take only the largest principal components. If we want 4 handles as a result, then we can take the top 4, the 4 largest dimensions, and that'll give us an initial guess for our flat for the subspace which passes through all of these vertices. Okay, so if we use this and we use an explicit expression for the flat as a weighted sum, then we get this expression. So F times W tells us gives us a transformation matrix, and so this expression here is measuring the error of applying the transformation matrix to a vertex. And looking at the data that we are given. And if we look at this expression, it's quadratic in F, it's quadratic in Wi, and it's also quadratic in Vi. But this F and Wi are the parameters for our for the flat that we're looking for, where our handles lie. And so our proposed solution is to do this in a global local way. So the local steps Wi are finding the closest point on the flat, and then the global step is finding a new flat F, which passes as close as possible to our estimated points. And so this ends up as a linear matrix equation, which, because of redundancy, reduces to a 4H by 4H system of equations, and And so we propose to do this in an alternating way. So let's visualize this optimization. So let's go back to a space we can visualize. So we have a cylinder, and the cylinder has 4 handles, and we know that the simplex formed by these 4 handles must form a tetrahedron at some point, because there's only 4 of them. But essentially, that tells us that there's a tetrahedron with 4 handles that lies in a 3-dimensional subspace. So what we can do is we can visualize the closest points on this 3-dimensional subspace. So we're gonna be visualizing the projection. So we have a 3-dimensional subspace. This 3-dimensional subspace is all possible transformation matrices that can be applied to any vertex. And we're going to be visualizing the vertices of the cylinder projected onto the subspace. And the subspace will be changing as the optimization happens. Okay, so using our initial guess, this is what the optimization looks like. So this is a weird subspace. This is I can't visualize 12p dimensional space. I can visualize 3D space. We're visualizing the 3D space we're visualizing is itself. The 3D space we're visualizing is itself being optimized. So we're visualizing an optimization which is affecting the space that we're visualizing the space itself changing under optimization, and all of these points are the vertices of the cylinder. Now, what we expect to see from this cylinder, because the cylinder has this straight line skeleton along it, each vertex is a weighted average of only 2 transformations. And so that's what we're seeing here during this optimization. Every vertex ends up on a line between 2 of the transformation matrices. So we can see we can see there are 1, 2, 3, 4 corners here, and those 4 corners are the handles themselves, and then the weighted averages are the tetrahedron that they form, and in this case we know that the cylinder vertices lie really along the edges of the tetrahedron. So from this, I would say, all right, well, we're doing pretty well. This is about 10 iterations and things stop moving. So I should be satisfied with our solution, and I should be satisfied with our initial guess. Here's optimization from a worse initial guess. So again, we're visualizing a 12p dimensional space. We're visualizing it because we're visualizing it because we can visualize 3 dimensions of it. And here, that's our same optimization, but running from a worse initial guess. It still converges. It takes a lot longer, around 300 iterations, but it still does converge. Finally, that initial guess is still important. This is what it looks like to optimize from a random initial guess. There's like some structure in here that I can see, but I don't know what to make of it. And it just sort of starts rotating and rotating very slowly and rotating very slowly. And it's going to continue doing this and run, which is over 10,000 iterations. It looks like it's not really making progress. I don't know what to make of this because the previous worse initial guess I showed you, there was also a few hundred iterations where very little was happening, and then suddenly it clicked into place. So as far as I'm concerned, this is stuck. But yeah, so the initial guess is important, but given a pretty good initial guess, we were able to recover low error solution. Now I'm just kind of comparing 5, 10, 20 iterations and ground truth.
So Yotam, in the previous one, where
yes.
You had a bad initial guess that converged, did it make sense geometrically? Like the
Yes.
Okay. Let's see.
This, like, you mean what the initial guess was, or this visualization?
No,
I see one point. Do you see this? Yeah.
Yeah,
Like I see, you know, like we're looking at is we're looking at like a rotation, right, of a three-dimensional space inside of a 12p dimensional space, and these points projected on it. There's this one point that's really, you know, traveling a lot. So I think the rotation must be around, you know, must be affecting that point.
but can you trace it back to the original geometry? Like, I think part of the problem here is it's the visualization is challenging, right? Even in this
Yes.
case, when
Yeah.
you only have like 4 points, 4 handles.
Right. Right. Like it's hard to do something simpler than this case.
Yeah, exactly. But then maybe if you show the geometry, like what happens to geometry in parallel to the optimization, then it might be a bit more intuitive to figure out. I don't know.
Yeah. The problem is I don't know what's happening to the. Let's see. Uh, right. I guess we could take the
You can take the
vertices and
transformations. Yeah,
right, right. We could apply the transformations directly. That's right. That's right. I don't need right because at this point we don't know the rest. We know the weights, you know, and the handles, but that's fine. We don't need them to visualize the geometry. Yeah, you're right. We could have visualized just every vertex with this
just
transformation.
yeah, it might give some insight as to what's going on. Because otherwise, I think this is like happening in a whole different space. So it's hard to kind of
Right,
yeah.
right, right. Yeah, like in this random initial guess, it's like I see these sort of. It looks like you know these. Looks to me like there are these tubes, right? They're these cylindrical
Yeah,
tubes, and I think those are like kind of around the edges, but I'm not sure. Yeah, yeah, that's a good idea. That's a great idea. Yeah, if we visualize the 3D geometry, we might see which points are close to the right place and which points are quite far away.
yeah. Okay, thanks.
Thank you for that. Yeah, so I'm going to say this is still an open problem, and I'm going to say that so in general, we don't have, we don't always have zero error solutions. If you come to a mesh animation that wasn't created with linear blend skinning, then uh, there's it's not reasonable to expect that there's a zero error solution. It's not reasonable to expect that there is a linear blend skin rig which will perfectly reproduce it. If it behaves very non-rigidly and so on. But if you come to me with a linear blend skinned rig and you demonstrate animations for me, it would be nice to recover them. And so these three examples are all that. So the cylinder that we saw previously is the here on the right, but these other two are sort of more complex. And so what do I want to show you? The algorithm that I just described is this blue curve, and you can see it in all three of them. It makes fairly rapid progress and then really levels off. Even on the example we just saw, you can see it makes rapid progress. This is, the full width of each plot here is about 20 iterations. So um, the other approaches that we tried from this how not to minimize flat distances are all of these other curves, right? Now, there's one in particular here for the cylinder with four handles, which is again like the simplest one we can do in 3D. Um, the a trust region, like a Hessian-based trust region approach, actually does achieve the ground truth solution in around 10 iterations. It gets superlinear convergence and does that. It takes hours. It takes hours just to do these like just to do 10 or 20 iterations, whereas ours does it in a few seconds. So it's not satisfying for that reason. It just doesn't scale to larger problems very well, and it didn't achieve the superlinear convergence for these other cases. But this is sort of like evidence to me that there are better strategies exist. Somehow, like the alternating local global steps are just like not right directions at each time to make better progress. It's also important to for yeah I also want to well, I'll emphasize it in a moment. So now we've talked about steps 1 and step 2 to estimate these vertex transformations in this subspace. So now we have this subspace, and we have the vertex transformations in the subspace projected onto the subspace. And now what we want to do is find the handles. So the handles should be a simplex, which encloses it. And what we want to find is a nice simplex. And a nice simplex is, I will argue, is a smallest enclosing simplex. Actually, I'm not going to argue this. I'm going to let the hyperspectral imaging community argue this. So in the hyperspectral imaging community, they have this following problem statement that they look at a lot. So satellites capture high-dimensional data from far away. It's high-dimensional because they may be looking at various spectra of light, not just the kind of red, green, and blue. So they're capturing this high-dimensional data across various spectrum of light. And what they know is that pixels contain mixtures of objects, particularly because of resolution issues. So for example, a single pixel may include a little bit of a tree and some smoke, or it may include some buildings and some vegetation, or it may include people along with cars. So there's each pixel is mixed, and this community asks the question: well, what are the objects? They call these end members, and what are the mixtures observed in each pixel? And they call these abundances. So in our terminology, these are handles and weights, or vertices and weights. And in their terminology, it's abundances and end members. But this problem, the idea of trying to find a minimum volume enclosing simplex for the data in high dimensions is an old idea. Actually, it's due to Craig from 1994, and the algorithms basically start with, you have these points in high dimension, you perform PCA, you choose the dimension that you're of the number of objects you think are present, the number of end members, and then they try to find the minimum volume enclosing simplex. And so we can just to visualize this here, if here are some points in 2D, this is what the convex hull looks like, and this is what a minimum volume enclosing simplex looks like. And so one interesting observation here is that you don't even have to observe any pure pixels. So you don't have to observe any pixels which are purely vegetation or purely buildings to be able to disentangle buildings with vegetation, assuming that there's a unique solution for this problem. And in general, and this problem is very well studied. I think there are even more recent approaches by now. In theory, it should be difficult. So in theory, there are infinite infinite families of solution spaces, infinitely, infinitely many local minima. Those local minima can be families of solutions and so on. Although the approach works well in papers, but in theory, actually, it gets easier the higher the dimension. There are actually some theoretical results that come from both this community and the non-factorization. It ends up being mere theoretical proofs, which were saying, you know what, so long as a big ball or circle you can fit inside of the convex hull of your points is larger than some factor, some length related to the dimension, the radius is greater than some length related to the dimension, and there's some points which are sticking out, which prevent this simplex from rotating, then there actually is a perfect solution that can be recovered. So I think that's why it works well in papers, which is still sort of in the absence of maybe proper real-world noise.
So sorry for interrupting again. But it seems to be closely related to the convex hull, right? Which is known to explode in higher dimensions, I think, if I remember correctly.
Yeah. The convex hull explodes in higher dimensions. It's much easier than the convex hull because there are only d+1 dimensional points involved.
Yeah. So I see. But do people use it to as kind of initialize a convex hull? Because here at least it seems like a convex hull will be a subset, like will be enclosed within your simplex.
Right. I don't know about let's see, convex hull in high dimensions.
I don't know if this is like a
relative-
specific example, or maybe in high dimensions it doesn't work.
Yeah, I mean, in high, it's what things about properties of the convex hull in high dimensions that come to mind. Uh, it's true that any projection of the convex hull to lower dimensional space, like any vertices of the convex hull, if you take your high dimensional points and you project them to a lower dimensional space, and then you find the convex hull of that. So in the simplest case, if you were to take your points and just look at any single dimension of them, and then compute the convex hull, which is just a min and a max, then those points. No, how does this work? Those points lie on the convex hull? They can't lie on the convex hull. They lie inside the convex hull, for sure.
Yeah, I don't know. Maybe it's not really. I didn't mean
Yeah.
to derail you.
Yeah,
I'm sorry. I just wondered if there's
yeah.
something.
I can tell you when we first started looking at this problem, we thought, let's compute a convex hull.
Yeah.
And then we thought we'll compute a convex hull, and then we'll have like some handles, And what we realized when we worked from linear blend skin rigs, where we could start with the ground truth data, right? We could start with the ground truth data. Our algorithm just suddenly was like converged in like one iteration, and always with a simplex number of weights, a simplex number of vertices, and we were like, wait, what's going on? Or this is and then like we kind of realized like wait, we don't need a convex hull. Like the handles, it must be a simplex. Like handles must form a simplex.
Right. This is very cool. Yeah, nice.
So so then we said, okay, the handles must form a simplex. So really we're just looking for a simplex. We don't need to the convex hull is like impossibly hard in high dimensions, but in the if we oh no, right, we were never able to compute was converging directly to the number of non-zeros equal to the number of handles and giving us essentially a simplex structure. And then we came across all this work that people had already looked at on minimum volume enclosing simplices. So some of this we started to develop independently, and then we ran into what these people were doing, and which was very helpful, as I'll mention in a moment.
Yeah.
So the minimum volume enclosing simplex problem, we can write this formally as saying, all right, we're going to have a matrix C where the matrix columns are the vertices of a simplex, and these are unknowns. So we're looking for an unknown matrix. We'll put these in homogeneous coordinates. So if we're in 2 dimensions here, we're looking at a triangle, so I'll say 2 dimensions. Then we're looking for vertices of a triangle. So we're looking for 3 vertices, and so that's a 3 by 3 matrix because the 3 vertices we add the homogeneous 1 at the bottom. So we're looking and we want to find the minimum volume enclosing simplex. So what does that mean? The volume of this is is the determinant of C with I think a constant factor in front, related to the dimension, so we can ignore that. So we're trying to minimize the determinant of C, subject to the weights are positive, right? So all of these, to compute the barycentric coordinates given the vertices of a simplex is as simple as C inverse times D. That gives us the barycentric coordinates, the weights. So we want them all to be 0. So this is a constrained minimization problem. Minimize the determinant subject to linear constraints here, and also that the bottom row of the matrix should be 1s so that we have homogeneous coordinates. So easy, should be easy. The determinant blows up in high dimensions, so that's not a great solution. That's not a great idea. But what we can do is we can compute the log. Right. The other problem is, of course, that we have an inverse. These are not linear constraints, since we need our matrix inverse. So what we can do is we can invert C, and call that x, and then we can maximize it, maximize the determinant. And so we'll minimize the negative log determinant. The log determinant behaves, it's actually fairly easy to compute, and there are known formula for the first and second derivatives even, so we can compute a Hessian of this, no problem. Now we do have linear constraints, and we still have a linear constraint for our homogeneous coordinates, which is just, we still have a linear constraint for our homogeneous coordinates, which is just that the matrix times ones should give us back the identity, because the inverse matrix times this times this matrix should give us back ones. Okay, so with this in mind, we use like a relatively recent sequential quadratic programming approach, which just estimates the diagonal and diagonal majorizer, I think, of this. And that's what we use to compute our solution. So let's look at how well this works. That's it. That's everything. First, let's just look at some. And there's the ground truth, and here's ours with 30 bones. And they look quite similar. Here's a comparison to kind of state-of-the-art inverse skinning solution with 20 bones. And I'll kind of like zoom in here and call out a couple of areas so we can see in the kind of the thigh of the elephant. I'm using flat shading here, which really emphasizes the surface quality. You can see this kind of wrinkling with the SSDR solution. You can also see that the tail gets quite bent. And you can see this kind of undesirable sharp artifacts along the belly and the foot. And here's another example of the horse, a horse collapsing. And again, the animations look good. When we zoom in here, we can see, the SSDR has a lot of extra, wrinkling along the neck, undesirable wrinkling, the knees of the horse. Maybe those are the ankles. Yep. So, we have lower error. There's another approach from 2010, which assumes there are no more than 4 non-zeros. So it assumes this sparsity, that the weights are sparse. And can be desirable in real-time applications. And they exploit this times, but the error is substantially higher. And their approach is really kind of heavily dependent on those assumptions. So directly scale, removing that option. So yeah, so in that sense, we have very good error, lower error, and competitive running times. Faster than the SSDR, slower than the Kavan. Now the question is, do we recover ground truth? So I'm going to show this to you in stages. So we can recover the ground truth for this, some simple cases. So like the cylinder, these kind of four-bone cylinders, which I showed you, looks very similar to ground truth. It looks like ground truth. Yeah, and we do always recover the correct position. So if you look at the shape of the surfaces, they're in the right positions. But if we look at the the location of the these are like centers of masses of the weights, we see that those are not in the right place. They're not in the same place as ground truth. So we're recovering different handle transformations and weights. But if we kind of just just to make if we just want to evaluate the third step, the minimum volume enclosing simplex, we actually see that if we give ourselves, true per vertex transformations, it recovers everything. Like the minimum volume enclosing simplex idea really does work to give you background truth. It's just very sensitive to the quality of those positions, the transformations it's given. And so the final comparison I want to show is to this mesh animation compression, where yeah, I showed that one. Sorry. Where's this bottom one not playing? There we go. Now, yeah. So in this scenario, we don't really care about anything except the bits per vertex per frame. And when you use, a linear blend scanning to do this compression, you end up paying a one-time cost for the weights. You store some number of bits per vertex for the weights, but then every additional frame is just an additional affine matrix per handle shared by all vertices. So it leads to a very low incremental cost per frame, and we end up kind of substantially lower error than the state of the art. Yeah. Yeah. So before I conclude, you can find code and data on our website, and I'm grateful to various people with whom I had conversations about the difficulty of this problem, and financial support, and other authors who ran their algorithms on our data. And so to conclude the talk, I want you to walk away with this idea that inverse skinning is a problem in high dimensional geometry. There's a relatively simple expression for it that can be very hard to visualize. Maybe it's, I'll try Mary's idea. And if people in the hyperspectral image unmixing community make advances, then we'll have better performance. And if people work on this closest flat problem, essentially the closest to a set of lines, but in higher dimensions, then this will also greatly benefit this problem. Just a few limitations. So the transformations we were just transformations. So if you want users to manipulate them, they're a little less intuitive since they're not necessarily rigid. They can have scaling and so on. We don't consider sparsity. Sometimes people want this, but it's not always automatic. LBS weight solutions generally don't generate sparse weights. Sometimes they do. And we also don't recover like a skeleton. We're just recovering handles in the abstract. Yeah. So thank you.
Thank you. Thanks, Yotam, for the great talk. It was really nice to see all these